Both the topics are important from the exam perspective. Good morning, students. Welcome to this session. And in this session, we will look into the regression. In the last class, we looked into the decision tree and how we can solve problems or come up with a model for solving the any kind of a classification related problems. In that, we saw what like two examples, whether outdoor play should be allowed, yes or no. And there was one more problem we looked into, whether the particular person should be given with a loan approval, yes or no. Those two scenarios we saw, and for more details, you can go back to the previous recordings, and you can get more details. Now we look into the regression. What is a regression? Regression is a modeling technique used for the prediction. What is a prediction? For example, you want to predict the value. Okay, predict the what would be the future value for certain thing. For example, if it is a stock market, like every day the stock trading happening, and there is a price at which the stock will get traded at every day, and you want to predict the stock price, maybe a week after, maybe next hour, or maybe next month, so on. So that prediction is like related to a problem, so where you want to do the prediction. For example, like you want to predict the sales figures in particular company. So that based on the historical data, you can train the model and you do the predictions. It is well-known statistical technique to model the predictive relationship between several independent variables and one dependent variable. So what the prediction is, we are going to predict about one dependent variable. So you can say this as a dependent variable or a target variable. That is the value we are going to predict. And how that prediction is done? The prediction is done based on the some set of the independent variables. Based on these independent variables, you based on their values, you will predict what could be the value of the dependent variable or the target variable. For simplest example, y is equal to mx plus c. You are already aware of this. It is a equation for the straight line. So let us assume that your data points are in such a way that the best fitting curve is the line, straight line, y is equal to m into x, mx plus c, where x is the independent variable based on which you are going to predict the y value. That's why we have y is a dependent on the target variable. Y's value you are going to predict based on the value of the x and value of the m. And what is the m is the slope of that particular line, best fitting line. And c is the so it is a interception on the y-axis, interception of the line on the y-axis. So that is how, that is the best model that I can come up with a certain data points, y is equal to mx plus c. And this particular equation is going to explain all the data points that are available on the training data set with some kind of a error. So the predictive value, the accuracy can be, we can figure out what would be the accuracy. And the same model y is equal to mx plus c can be used for predicting any unknown value. Suppose let us say we have x value which is unknown. We can use that unknown value and put it in y is equal to mx plus c, and we already know the what is the value of the m and what is the value of the c. That defines our straight line. And by substituting the value of the independent variable, that is x, we get the y value of the y. That is the prediction that we are doing. The objective is to find the best fitting curve for the dependent variables in multidimensional space. In case of a regression, always our objective is to find the best fitting curve. It could be a straight line if it is only two variables are there. that is one independent variable, one dependent variable, independent variable on the x-axis, dependent variable on the y-axis. It forms a straight line. And if you have two independent variables, it will form a plane. And if you have more than two independent variables, the dimension of the curve, it will keep on increasing. That is how each independent variable forms a dimension. Whenever you have like two dependent variables, it's like we have a two dimension associated with predicting the values. If we have three variables, we got one more dimension, three dimension, to predict the value of a particular variable. And the resulting curve could be a linear curve or a non-linear curve. It depends on what is the relation between the independent variables, and whether it is a linear relation or a non-linear relation. Based on that, I will get either curve as a linear curve, or I will get a non-linear curve. The quality of the fit can be measured by the coefficient of correlation R. Uh, uh, what is the measure? One of the measure for measuring the quality of the best fit, what you have found, the curve, that best fitting curve you have found, by finding the coefficient of relation, that is R. So we will find out we'll calculate the value of the coefficient of correlation. It value will represent the quality of the best fitting line or the best fitting curve. And higher the value of the coefficient of correlation, that shows it has a better explains the given data points. The key steps for regressions are listed as below. List all the variables available for making the model. So whatever the problem statement you have, according to that, you have many variables that are available for making the model. And among those variables, we have to select, establish dependent variables of interest. Means if you want to predict the stock price, then stock price is the target or the dependent variable. And if you are predicting a sales figure, then that sales figure is the dependent variable. So we have to establish what value we are predicting and what variable we are predicting, and that variable will become the dependent variable. And we should have examine visual relationship between the variables of interest. Visual relations is like plotting a graph, plotting a bar chart, some kind of a heat map. There are many ways we can find the relationship between the variables. Why we have to find the relationship between the variables, especially independent variables? In case of a regression, we don't want to have two variables who are correlated. Means that is called as a collinearity. Means the two variables that are present, their behavior is exactly the same. They are highly correlated. Means if one variable increases, the other variable also increases. If it decreases, then the other value decreases. In such cases, we don't want to consider both the variable for the doing the predictions. If we consider both the variable, then the resulting model will have a less accuracy, and we could see like a accuracy deteriorating, and we will not know like why it is happening. That is called as a effect of the collinearity. So we want to avoid collinear variables. By looking at these relationship, right, between the variables, we can find out some of these variables, and we can pick the best among them for our prediction purposes. For example, I would say like in the given data, let us say you have like medical data, and we have date of a birth of a particular patient, and also we have the age. These two are highly correlated, right? There is a particular relation between the date of birth and the age. With respect to the current year, the distance between the objects is going to increase, so that behavior will be exactly the same. So number of years is going to increase. In such cases, we don't want to take the both the variables, which will make the model inaccurate. We want to consider only one. Find a way to predict the dependent variables using the other variables. So we have to find a technique how we can predict the dependent variables value based on the independent variable data. Statistical relationship are about which elements of data hang together and which ones hang separately. So, what is the statistical relationship? Which are the data elements that go together? Hang together is like they go together, and which ones they do not really go in hand. So, those kind of relations, statistical relationship, we have to find out. And one of the key thing that is used for finding such a relation is a correlation, right? We can find a correlation between two variables. There are multiple kind of a relation between the two variables. Either when we say correlation, two variables are correlated, means as one increases, the second one also increases. As the one decreases, the second one will also decrease. That kind of a relation is called as a like a positive correlation. Okay. For example, we can say like as the sales figure increases, the profit also increases. So they are highly correlated. Uh, there are certain other things which are not related. So suppose I have a age and salary. Okay, so they may not be related as much as the relation between the skill and the salary, right? There are certain things which will have no relation between them, and there are certain things which will have a like a opposite relation. Means as one variable increases, the other variable decreases. As the variable decreases, the other variable will increase. For example, let us say we have a train which is traveling from station A to station B. The speed of the train is like inversely related to the distance between the two stations. As the speed increases, the distance between the two stations will decrease. So that has a kind of a inverse. Suppose if the speed reduces, distance between the stations will increase. So that is a kind of a inverse relationship. So that kind of relationship we have to figure out in case of like before doing the actual model. It is about categorizing the variables that have a relationship with one another and categorizing the variables that are distinct and unrelated to other variables. Why we want to do this is like we want to find out the variables which are correlated, means whose relationship follows the sentence increases, the other one increases. We won't don't want to consider such kind of variables. Like I don't want to have both of them. I will just have only one. And we want to, our main aim is when we are selecting the independent variables, we want them to be totally distinct and unrelated. Means one variable do not have any kind of a relationship with the another variable. So that will increase the predictive power of these elements, because I have variables which do not have their relation between among themselves, but they have an influence on the output, that is the predicted value or the dependent variable. That is the reason we want to have a distinct and unrelated variables that will increase the predictive power of the our regression model. It is about describing significant positive relationship and significant negative differences. So that is what I said. Two variables moving in the same direction will have a positive relationship between them. Two variables moving in the opposite direction will have a negative relationship, and two variables not at all related are like a totally distinct and unrelated variables. That is the kind of relations we can have. And first and foremost measure of the strength of shape is a correlation. So correlation is a very powerful measure that we can use to find the relation between the two variables. The strength of a correlation is a quantitative measure that is measured in a normalized range between 0 and 1. So it is a correlation is a quantitative measure, and this measure will tell us the range is between 0 to 1, and it will tell us the relation between the two entities. 0 meaning they are not at all correlated, there is no relation between the two variables. 1 being they are highly correlated, so they have a very a solid connection between them. A correlation of 1 indicates perfect relationship where the two variables are in perfect sync, and correlation of 0 indicates there is no relationship between the two variables. Then the correlation can be a positive. So once we have a solid relation, that solid relation can be positive or that can be negative. When two entities are having a solid relation and positive, that is plus one, they move in the same direction. One increases, other increases, one decreases, other increases. Or they can have an inverse relationship, even though they have a very strong relationship, but it is inverse. As one increases, the other will decrease, and vice versa. So those are a negative that we can represent with a minus one. The variables move together in the same direction or opposite direction based on whether they have the positive or the inverse relationship or the negative relationship. Therefore, a good measure of correlation is the correlation coefficient, which is the square root of a correlation. So one more measure that we are going to use is the coefficient correlation coefficient, and this coefficient is represented by the lowercase r, and it can range from minus 1 to plus 1. And so minus 1 to plus 1 is the it's a range. Minus 1 indicating the solid relationship, a strong relationship, but inverse relationship means they move in the same direction. 0 being no relationship between the two entities, and plus being a very strong relationship but in the positive direction. R value of 1 shows a perfect relationship in the same direction, and R value of a minus 1 shows a perfect relationship but moving in the opposite direction. So we can calculate the coefficient, this particular coefficient of correlation using the given formula. In this given formula, you can say R is equal to x minus x bar into y minus y bar divided by square root of x minus x bar square into y minus y bar square. Now, what is the x bar here? X bar is the mean value of the x values, and y bar is the mean value of the y data. So how to find the x bar? A simple formula, like if you have like a 10 elements, okay, x1, x2, x3, and so on, x10. What would be the x bar? X bar is equal to x1 plus x2 plus x3 plus so on plus x10 divided by 10. So if it is n element, x1 plus x2 plus x3 plus x4 plus so on plus xn divided by n, where n is the number of data elements that we have. X is the mean of the our y element. Okay, same function. Y is equal to y1 plus y2 plus y3 plus so on until plus yn divided by n. So using that, I can find a numerical value of the coefficient of correlation. So these are the some of the visual look of the relationship between the two entities. First one in the A diagram, you can see there is a clear linear relationship is there. If I fit a best fitting curve here, maybe it would be a straight line, right? A straight line like this, which will explain most of the data points. And similarly, if this data point, so it is x and y, it is showing a positive relationship. So as one entity increases, the other also increases. So this is a perfect, I would say it is very close to plus one. And this is again a linear relationship, but here you can see it is like a opposite, as you can see like as the one decreases, the other one also decreases. This is a curvilinear relationship. Maybe the best fitting line would be something like this, right? Which goes through most of the lines. So this is a curvilinear. It's a non-linear relationship. And another example of curvilinear is this one. So it depends on what would be the best fitting line, and accordingly your accuracy will be predicted. Now, if you can see this one here, the data points, there is no clear relationship. Here visually you can make out like some pattern is there. Here is some pattern. This is some pattern. This is some kind of a pattern we have. Okay, it's a curvilinear, but there is some kind of a pattern. If you look this one, you cannot explain this data, right? This is like a totally unrelated. This is another example that shows there is no relation between the two variables. Okay, regression in this exercise, regression model is described as a linear equation that follows y is the dependent variable being predicted by the x, which is an independent variable, and it is also called as a predictor variables. So all the independent variables are called as the predictor variables, and there might be many predictor variables. For example, right now we have taken the only one predictor variable. There could be many x1, x2, x3, x4, so on. Then we can have a regression equation using all those predicting variables. However, there can be only one dependent variable because we are predicting. So when we are predicting, it has to be only one value that we are going to predict. Suppose if you want to predict any other value, you have to build one more model, isn't it? Right? When you are doing a prediction, always it is about a one variable, what value. Either it is a stock price, you're going to build a separate model. Let us say if there is any stock related entity, and you want to do the prediction, again you have to build a one more model. So dependent variable is always only one, and it will do the particular prediction. Here every model that we have can be with suppose one predictor. It can be put it in the form y is equal to mx plus c. In this case we have used y is equal to beta naught plus beta 1 x plus epsilon, where beta naught and beta 1 are the constants, and beta naught, as we told, it is a interception on the y-axis, and beta 1 is the coefficient of the x variable, and this plus epsilon is some random error variable. And suppose if you have more variables here, this is actually exactly the form of the straight line. Y is equal to mx plus c, and we have included the random error variable. Here it is represented as a b naught plus beta naught plus beta naught 1 x in plus epsilon. Suppose if we have more variables, so always it is highly inaccurate model to just have one predictor variable and it will predict the output. In reality, in realistic model, we will have like a n number of predictor variable. That kind time the equation would be y is equal to beta naught plus beta 1 into x1 plus beta 2 into x2 plus beta 3 into x3 plus so on plus beta n into xn plus epsilon. So that is the equation where beta 1, beta 2, beta 3 are coefficients of a x1, x2 and x3 and so on. This is one example that is given, simple example of a regression equation. I would predict the house price from the size of the house. So this is the data given. Based on the size of the house, we have to predict the what would be the house price. So here size is a predictor variable or the independent variable, and house price is the dependent or the target variable. based on the what size we get as an input, we are going to predict the what is the value of the house price. So we have all these data elements, and if we plot all those data elements as a scatter plot, x axis being the size in square feet and y axis being the house prices, okay, represented in thousands of dollars, and whatever the data points that have been given here, those are plotted here. So you can see all these are the data points which corresponds to the size and the price. And if you look closely at this, maybe we can fit a linear, there is a linear relation, and we can fit a line which is will be of the form y is equal to beta naught plus beta 1 x. So x being the size, y being the house price. Visually, one can see a positive correlation between the house price size and the square feet. So you can see there is a positive relation. As the size in square feet, as the size is increasing, you can see the price is also increasing. However, the relationship is not perfect. Running a regression model between the two variable produces the following output. So if you run a regression on top of that, this will produce a this particular stats, where r is equal to 0.891 and r square measures explains the how best that best fitting curve explains all the data points. So excuse me, it explains the best fitting curve that we have found out. It explains about 79.4% of the data. Then these are the coefficients. Intercept, so intercept is beta naught, okay, beta naught is minus 54,191, and this is the coefficient of the size. If you consider this as x, this is beta 1, and what would be your model or the equation? House price y is equal to beta 1 into x. What is the beta 1? 139.48 into x, then plus beta naught. In this case, beta naught is minus 54,191 minus 54,191. So this particular equation is can be used for predicting the house price value. Now you input any square feet area, it is going to tell you what could be the what is the predictive price using this particular model. This equation explains only 79% of the variance in the house prices. Now, in your book, these things are the analysis has been done in the background, and directly they have given these values. For your understanding, what I have done is I have used the Excel, simple Excel, and I have shown you how we are going to get these particular values. Okay, this is sheet 1. So if you see this particular diagram, it is very similar to what we saw here. I use the same data points. You can see this data points, this being x and this being y. Just I have reversed that. So here I have all the x values, size, square feet, and house price. This is the value we are going to predict. And if you see the same values I have here, okay, it's difficult. So 1,850 to 29,500. So 1,850 to 29,500. Last value being 2,240 to 56,800. 2,240 and 250, 25,000, 256,800. On this plot, I have plotted the chart, okay, scatter plot, and scatter plot will look like exactly this. I'm not sure what the author has used for the analysis. There are many tools that can be used for performing the regression. Here I am used the simple Excel. Now on this, once we have this, I can run a regression on this, and regression will get me the best fitting line, and the best fitting line. These are the the summary that gets outputted from the regression analysis. Regression statistics, you can see R value as 0.8911, 0.891, and R square is 0.794. 0.794. And there are some other statistics you may not understand as of now, which is not part of your syllabus. We are more interested in the coefficients. So intercept, you can see minus 54,191, that is beta naught, minus 54,191, and beta 1, coefficient of the x variable 1, that is 139.48. That is 139.48. That is how we are able to write this equation. Now, just to show you like how we can come up with this kind of a data, I will just demo that for this one particular case, and the rest you can create your on your own. Just I will show how the outputs we get it. I will copy this data and open a Excel, put the data somewhere. Now you can use data, and that is for the analysis. I would say insert. Then you can see the scatter plot here. Okay, I would say scatter plot, and I will use this for scatter with only markers. Now you can see this one. Just I will move it on the other side. I selected this data, then accordingly it predicted all these values. So you can see house price, and this is the size. This is the dependent variable, and this is the this is the independent variable or the predictor variable, and this is the dependent variable or the target variable. And if I want to run the analytics on top of that, you can click on the data, and we have data analysis. Then you can select from this list, you can select regression. Okay, you can see regression and say okay. Then you have to give the input y range. What is the y? Y is the dependent variable or the target variable. Give the where the y value is present. This is the complete y variable, and input x. Input x. Give the range of the x. Give the range of the x. Then rest of the things just keep as is. You can see here it has created a 1 second. I will say control side. It went on to another sheet. So what I will do is once again we will go to the data analysis. We forgot to give the place regression where the output should be shown. By default it's shown to a new worksheet, so you can put it on the same worksheet. Output range, I will say put it here, right? This value I have given. Okay, so this is the output range. Earlier it was new worksheet, that's why it created a new worksheet. If you want to see everything on the same sheet, then you can select this output range and say okay. Must contain at least one data point. Okay, so mistake is, once again we will do that. This is the range for the y, and let us say, let me redo this x-axis from here to here. So that is the range, and output range, once again I will select it. This is the output range. Now everything is set. Rest of the values, let it be like that. You say okay. Now it will plot the same thing here. Now you can see what I have is this 0.891 and r square. That is what we got in the what has been shown in the textbook. These are the values, and if you see the coefficients, this is minus 54,000 and this is 139.48. So this is how I get the equation. So what would be the equation here? y is equal to, okay, the value of the m is 139.48, or you can say beta 1 139.48 into the size of the house minus 54,191, which is what we got in this particular equation. Suppose earlier prediction we did it the one independent variable. Whenever we are doing the prediction with just one independent variable, the accuracy would be less. As I told you, if you have more predictor variables which are unique, means they are not dependent on each other, they don't have any kind of a relationship among them, then the predictive power will increase. Here in this example, we have added one more predictor variable, or the independent variable number of rooms, and now based on the size of the room and number of the rooms, we are going to predict the house price. And if you perform the analysis, now it is going to be a three-dimensional, right? We have two dimension for the independent variables and one dimension for the dependent variable, so it makes a three-dimension. You can use any kind of a plotting which supports the multi-dimensional scatter plot. And after that analysis, we get this particular this is the correlation values. House price and the house price, obviously one, correlation is 1. Size and the house price 0.891, and rooms and the house price, you can see there is a very good relationship, very high correlation between the rooms and the house price, which is good, so that we can have better predictions. And also, if I see rooms and the size, we have like, we don't want to have this as a very high value. If we want to if we get this as a very high value, then what that means is we can use only one of the two variables, right, by for the prediction. If we have this towards zero, that is very good scenario, that makes a good candidate for being a predictor variable, because it is independent from the other variable. Now, if we get the value of the R, we get it as 0.984, and R square 0.968. So almost 97% of the data points are explained using these two variables. And if we see the coefficients, the intercept beta naught 129, 12,923, and size of the square feet, that coefficient beta 1 is 65.6, and this is beta 2. Beta 2 is 23,613. Okay, so this is the how I can write the equation now. The house price, that is y, is equal to beta 1 x1, that is 65.6, into size. Size is the first variable, right? Size is the first variable, into size, plus beta 2 into x2. Beta 2 is 23,630, into second variable x2 is nothing but number of rooms. So number of rooms plus beta naught, that is 12,923. So I don't know why it is 924. If I show it from our Excel sheet, same data, I copied these two, one more element, that is number of rooms. Now I have two predictor variable, and then I perform the analysis. When I do the analysis, this is the summary of the regression. R value comes as 0.984, which is same as here 0.984, and R square is 0.9688, which is exactly same as this one. And these are the coefficients that we get. The coefficients is intercept, we get it as this is beta naught 12,923, and beta 1, that is the coefficient of the size. Okay, the size, we get it as 60.56 into size, then plus 23,613, that is the coefficient of the number of rooms. So that is how we get this particular equation. Next, nonlinear regression exercise. Uh, Always, what kind of a relation the independent variables and the predictor variable will have is like either linear relationship, or it could be some kind of a non-linear relationship. If it is a non-linear relationship, then we have to have a particular a non-linear curve that will best fit the given data point, so that we can do the correct prediction. The relationship between the variable may be curvilinear. For example, given past data from electricity consumption in kilowatt hour and temperature, the objective is to predict the electrical consumption from the temperature value. So here are the dozen past observation. I will explain you what that means. So the given example here is the data that is available is we have the temperature and the power consumption. So you know there is a good relationship between the what is the outside temperature and what would be the power consumption for a city, or for a particular area, or for a particular country. It could be anything. So it depends on what kind of analysis you are doing. So we have on the x-axis temperature and in Fahrenheit, and on the y-axis we have the power consumed in kilowatts. Now, if and these are the data points. So this is the kilowatts consumption, and this is the temperature in Fahrenheit. Okay, so if it is for 46.8, it is 12,530. And if you plot these two things, this is how you will get. So you can see here, initially what happened when the temperature is low, right? When the temperature is around, this is like around 45 or so, the power consumption is high. It is like uh, maybe around 12,000 kilowatts. And as the temperature increases to 60 degrees, 60 degrees is like very optimum temperature, you can see the power consumption reduced. And as the temperature increases again, so it is getting hotter. So this side it is temperature is cold, and this is normal. When it is cold, the power consumption is high. When it is normal, power consumption is relatively less. When the temperature gets very high, okay, then the power consumption increases again. So this is a non-linear relation, and definitely we can explain this the behavior, because when the temperature is low, people will put on the heaters, right? When they put the heaters, the amount of power consumed will be very high, and when the temperature gets to the normal, then they don't need any kind of a heater, because that is the optimum temperature. Then the power consumption will reduce, because they will switch off their heaters. As the temperature increases, the people will start using the AC, right? When the AC consumption starts increasing with the temperature, the intensity of the AC that is going to be run will be very high. That explains that the power consumptions drastically increases. Now, if we try to fit a line, a linear line, it may not explain. You can see here, this is the linear line that is fitted into this particular data, and it doesn't explain properly all the data points, because the nature here is the curvilinear. So this particular graph shows the kilowatts and the temperature. Now we want to bring some kind of a non-linearity. Instead of using the temperature, we are going to use the square of the temperature and see. Now the next column you are going to put is the square of the temperature, that is temp square, and you are going to square and put this value, and you are going to plot the kilowatt consumption against the square of the temperature. Now you can see here, now these are the square of the temperature and the power consumption data points. You can see almost we can put a straight line. Now, with a non-linear regression exercise, if I put the non-linear curve, then I will get this kind of a stats. So if I say I will have one predictor variable as temperature, another predictor variable is temperature square, and then I'm going to fit the model. So you can see R value is very high, is 0.992, and R square 0.984. Now that means this kind of a curve, whatever I have created the curve, it is going to explain 98.4% of the data points. So that is a very, very good model. And what are the different coefficients I get? For the intercept, I get 60, that is beta naught, 67,245. Temperature, for the temperature, coefficient is beta 1 minus 1911, and this is for the temperature square. It is beta 1, beta naught, beta 1, and this is beta 2. It is 15.87. If I write the equation, y, that is energy consumption, is equal to beta 2 into the second variable, that is temperature square, minus 1911 into the first variable x1, that is temp, plus we get beta naught, that is 67,245. This is the equation that we get. Now I will show you from the Excel how we can get that. Now first, before proceeding with the okay, now before proceeding, we have this as a non-linear. We will try to fit the linear curve. We are not going to fit the non-linear. So I'm just going to take the independent variable x as only temperature, and I will try to fit a best line. So if I fit a best line, what you are going to get is r value is going to get 0.77, and r square value, you can see r square value is very, very less, that is 0.60. Only 60% of the data points are going to be explained. So that is why it is not a very good model. If I use a straight line here, this is the coefficient I am going to get. So our equation will be y is equal to beta naught, that is 185, beta 1, that is 185.27 into into temperature, plus 319. But this particular equation will explain only 60%, which is not a good model. Then we go for a non-linear relationship. So I will take temperature and the square of the temperature. You can see here I have equation put is A5 into A5. That is, this is A5 cell, this is the square, and then I have the kilowatt consumption. So this forms the x1. This is x2 variable. Two variables I have. Then I will fit the regression. This is what you are going to get. R is 0.99. This is what we got, 0.99, and r square is 0.9846. Okay, r square, and these are the
Hello, sir.
coefficients. Yes, hello.
Sir, screen is not visible.
Oh, screen is not visible.
Yes, sir.
Guys, earlier it was visible.
Yes, sir. Now it came, sir.
Okay, okay, okay. Thank you for telling. All right. Okay. So, okay. Did you see Diksha? Did you see the
Yes,
with
sir.
one
From
variable?
non-linear.
Okay, non-linear. So okay. So this, how we got this one is by using temperature and the square of the temperature and kilowatt. When I run a regression on top of this in Excel, I get a values like this. R value 0.99, r square is 0.984, and these are the coefficients. This is beta naught, beta 1, beta 2. 67,245, 67,245 minus 1,911, 15.87. So this is the analysis that we can do using the Excel sheet, and the similar values are shown in the your textbook. So this model, with this model, we can have the equation energy consumption is equal to 15.87 into temperature square minus 1911 into temperature plus beta naught, that is 67,245. Now any unknown value you put as the temperature, then you can predict what is the electricity that is going to be consumed. So this equation explains 98.4%. So 98.4% of the variance in kilowatt consumption for the given temperature. Next one is the logistic regression. The regression model traditionally work with the dependent variables that have continuous values. Now we saw two examples here that will give us a one is the house price which is a continuous value, and second one is the energy consumption which is a continuous value. So normally these regressions are used for the continuous value when the dependent variable is having the continuous values. However, we can use the logistic regression models that will work for the categorical prediction. Categorical prediction means what? You can use it for the classification problems. So prediction problems, what the output you will get here, for example, you put some temperature, right? You put temperature as 90 degree and you find out 90 degree 90 square into 15.87, then minus 1911 into 90 plus 67,245. You will get some value, that is the total kilowatt consumption at 90 degree. That value is a continuous value, isn't it? Similarly, house price, you put the size and number of rooms, it will calculate and it will give some continuous value. But we can use logistic regression for the classification problem. For example, a particular patient can have a diabetes, yes or no. Okay, we can use probability scores for doing that, but we can do this logistic regression for the categorical classification also. Either it is a binary classification or multi-class classification. However, logistic regression models can work with the dependent variables that are categorical. For example, predicting the patient being diabetic or not based on the age, gender, BMI, blood test, various other values. So we can have the dependent variables as a categorical also. So categorical means you are going to put it into different buckets. Yesterday we talked about the news articles. News articles can be bucketed into sports news, political news, then entertainment news, economical news, etc. Then logistic regression models use the probability score as the predicted value of the dependent variable. So they use the probability score, maybe like if it is a binary classification, if probability is more than zero point 0.5, it is classified as S. If the probability is less than zero point 0.5, it is classified as no, something like that. And if there are multiple class, if you remember, you have gone through many ML learning, machine learning models, we can use the softmax. Softmax will give a multi-class. Same, it is a probability, but it will assign out of the categories you have chosen, whichever is the highest probability, that will be the chosen class. The logic transformation is used in LR, this logistic regression, as the dependent variable. So you can see this is the general logistic function. This y-axis is the dependent variable and x-axis is the independent variable. You can see there is a very small bandwidth where the value will change either 1 or 0. So if the probability is more than the 0.5, this can be categorized as 1. So it's a binary classification, either 0 or 1. If for all the values you can say greater than 0, 2, 4, 6 for the independent variables, the output would be 1. And for values of the independent variable less than 0 and so on, the output predicted value would be 0. Regression models are easy to understand. They are built upon basic statistical principles such as correlation and least square error. It provides a simple algebraic equation that are easy to understand and use. So all these regression models, they are built on the simple statistical principles. Uh, what we saw so far is the correlation and least square error. Error is one of the methodology where you continuously try to fit a line and have a least square error tending towards 0. So it may not tend towards a 0. So based on certain cutoff, you will stop your analysis. And it provides a simple equations, whatever the equations you saw so far, algebraic equation. Such equations are provided as a models, and using which you can do the predictions, or you can do the classification. And the strength of the regression model is measured in terms of a correlations of the coefficients and other related statistical parameters that we are very well understand. For example, as we talked so far, we are selecting the predictor variables based on their correlations. If they are highly correlated, we are not going to select all the variables they are correlated. And when we are selecting the independent variables, we want those variables to be distinct from each other, so there is no relation. Then the predictive power will increase. Regression models can match and beat the predictive power of the other modeling technique. So regression models, relatively it gives a very high accuracy. And whenever you are beginning your analysis, so when you are working on the industrial projects or personal projects, you should always start with a regression model. So regression model, if you have any idea in your brain to solve certain problem using a ML model, start with the regression. Regression will give a good idea, and maybe then you can compare that results with the other models. Maybe regression will give comparatively better predictive data or the results compared to other models. But there are other sophisticated models such as ANN, which can work on a very complex problem, and it can give a very high accuracy compared to the regression model. Regression models can include all the variables that one wants to include in the model. Suppose if you want to have 10 number of variables, yes, you can include all those 10 variables. But again, you have to be very careful to make sure that all those 10 variables are mutually exclusive. They are not dependent on each other, or they do not have any kind of a relation among themselves. Regression models are pervasive. They are found in statistical packages as well as data mining packages. MS Excel also provides a simple regression modeling capabilities. So there are many tools. MS Excel, just I did the demo and I showed you how you can run the simple regression models with the given data. And there are certain disadvantages that are associated with the regression models. Regression models cannot cover for poor data quality issues. If data is not cleaned up properly, the model accuracy will suffer. Now, this is the most important thing. The data should be very clean. Proper quality of the data should be good, so that your regression model will be very highly accurate. So garbage in, garbage out. If your data is garbage, whatever the prediction model using the regression, it will predict the garbage, means it will predict very incorrect. Regression models suffer from collinearity problems. I told you about the collinearity problem. Collinearity is among the predictor variables, that among the independent variables, there are variables which are interdependent, means there is a relation between them. Such collinearity will have a huge problem on the predictive power of a regression model. You have to make sure such variables are identified and they are not taken as part of the predictor or the independent variable. Regression models can be unwieldy and unreliable if large number of variables are included in the model. So you have to be careful when you are including how many numbers. If large numbers, it is very difficult to figure out what is the relation between all those variables. So that can result in a very unreliable prediction by the regression model. All the variables will be included in the equation irrespective of their contribution to the predictive power of the model. So this is the one disadvantage. It doesn't check the predictive power of each of the variables, independent variable or the predictor variable. If you include it as a model, definitely it will be part of the equation, irrespective how much power it has, how much predictive power it has to predict the output. So that is the one disadvantage. Here care should be taken by the data scientist or the business analyst or the modeler to exclude such variables which do not have any predictive power, okay, from the equation. If you include them, definitely they will have some coefficient, and they will alter the predicted value, which will lead towards the inaccuracy. Regression models do not automatically take care of the collinearity. So as I told you, the collinearity has to be taken care by the data scientist. Next is the artificial neural network.